Hey guys, welcome back to the channel. After an unusually wet winter out here in California, spring has finally arrived. So I've been able to work on putting together this video in which I'm going to show you how I capture the spectrum of dim objects in the night sky. In this video, I'm going to show you the equipment that I use, and you'll see that there's quite a bit going on here, including a few DIY accessories that you might find interesting. I'll also show you how I use free and open source software like Nina or PhD2 Guiding to acquire high-quality scientific data. Tonight we're going to target a star and a planetary nebula. All right, let's get started. All right, let's start by taking a look at the equipment we'll be using tonight. If you have been a subscriber to my channel, you might recognize my telescope, which is an Astrotech AT130 EDT. It is a budget triplet refractor with a 5-inch objective lens open at f7. The telescope rides on an Ioptron CEM70 mount, which is itself set on top of an Ioptron tri-pier. Note that I use a pier extension because without it, it is possible for the spectrograph to hit the tripod legs when pointing near the zenith. At the business end of the telescope is my DIY 3D printed spectrograph called StarX. It is in its high-resolution configuration with a 2400 lines per millimeter grading and a 125mm objective lens. I precisely rotated the grading so that we can study objects around the H-alpha wavelength. The camera that I use to acquire the science data is a ZWO ASI 533mm Pro. So it is a cooled CMOS camera with very low read noise, very low dark current, and no M-glow. It is an excellent little camera and it also does not break the bank. The guide camera is a ZWO ASI 290mm Mini. To focus the telescope, I use a ZWO EAF electronic focuser. You might be wondering what this little telescope is doing here. It looks like a guide scope, but it is not. In spectroscopy, if you use a spectrograph with a slit, using a guide scope is not an option. You must guide on the slit itself. This telescope is actually an electronic finder scope which I use for plate solving. I used to plate solve the image taken with a guide camera, but at my focal length, and if you image a target that is sufficiently far away from the plane of the Milky Way, so that you don't have a lot of stars in the field of view, plate solving fails quite often, so using a small secondary telescope for that is very beneficial. By the way, I designed and 3D printed the brackets that attaches the electronic finder scope to my mount and it works amazingly well. On top of the OTA, I have my mini PC running Windows 11 and a Pegasus Astro Pocket Power Box Advance which combines a powered USB hub, a dew heater controller, and several DC jacks to power all of my devices. Tonight we'll connect to the mini PC using Microsoft Remote Desktop. Near the objective lens, this strange little device, which I also 3D printed, contains a small neon bulb. It generates light composed of a series of well-known emission lines that we will use to calibrate our spectra. This bulb is powered using 110V AC, which is generated by this box, itself powered with 12V DC. I designed and built this control box. The computer connects to it wirelessly using Bluetooth Low Energy. I even wrote an ASCOM driver so that this device appears as an ASCOM switch. If you would like to learn more about this project, check out this GitHub repository. Alright, everything is ready to go. Let's wait for the sky to get dark, but with the magic of editing, I'll see you in just a second. You're now looking at my mini PC. I'm connected to it using Microsoft Remote Desktop. It's pretty cold outside, but I'm inside the house where it's nice and warm. Let's talk about the software we'll be using tonight. So first, we'll be using Nina, a very popular free and open source image acquisition software for Windows. More specifically, we'll be using 3 instances of Nina. The first instance we'll only use in the very beginning to roughly focus the telescope so that we have a focused image coming out of the guide camera. This instance of Nina is connected to the guide camera and to the focuser. The second instance of Nina is connected to the telescope mount and to the camera attached to my electronic finder scope. We'll use that for plate solving so that we know precisely where we are pointing in the sky. And finally, the third instance of Nina will control our main imaging camera, as well as the spectral calibrator which controls our neon bulb, because we'll need to turn it on and off throughout the night. We'll also use a planetarium software called Carte du Ciel. As you can see, it is also connected to my mount via ASCOM. We'll use this software to point the telescope to our targets. We'll also use the iOptron Commander app to precisely center the target onto the slit using this control pad. And finally, we'll use PhD2 guiding to keep the target precisely on the slit during an exposure. I took this image a few minutes ago while the sky was still relatively bright. This dark horizontal line is an image of the slit taken by the guide camera. As you can see, it is incredibly narrow. It only measures about 6 pixels wide in my case. Once the sky gets dark, you won't be able to see the slit very well, so in PhD2 guiding, it is helpful to click on View, Spectrograph Slit, to display this little red rectangle. You can then adjust its position so that it's in the right place while the sky is still bright enough. Okay, we're all set. Let's start by focusing the telescope. I find it easier to focus the spectrograph if I point the telescope at a fairly dense star field. So let's go ahead and slew the telescope to an open cluster. We'll go to Messier 35 in the constellation Gemini. Once the telescope has reached its destination, let's split solve the image taken by the camera attached to the electronic finderscope using the second instance of Nina. Okay, now Messier 35 is perfectly centered in the electronic finderscope, so we can start an autofocus using the first instance of Nina, which controls the guide camera in the focuser. Alright, the guide camera is now perfectly in focus. In theory, because I carefully focused the collimating lens during the day, the image of the spectrum on the main imaging camera should be in focus as well. However, we can go one step further to refine the focus position and get as much flux as possible through the slit. To do that, we need to point to our first target of the night. It is a star, but not just any star. We are going to use Theta Leo, because it is relatively well placed in the sky right now, just east of the meridian, and it also happens to be in the MILES spectral reference database. During processing, we will use the spectrum of that star to calculate what we call the instrumental response, which will be critical to calibrate our spectra. We're back in Carte du Ciel. Let's locate Theta Leo and let's slew the telescope to it. Now let's manually center the target onto the electronic finderscope. Now that we've centered our target, let's go to PhD2 guiding and let's take a look. There's our target. We can use the control pad in the iOptron Commander app to approximately position our target on the red rectangle that represents the slit. Now let's start guiding. Once guiding has started, we can adjust the lock position so that our target is exactly centered on the slit. Using the third instance of Nina, we can now take a test exposure using our main imaging camera. Let's see what we get. And here's our first spectrum. Isn't this great? Let's pat ourselves on the back. Since we only need the area of the image that contains the useful signal, we're going to enable subsampling. And here is the final view of our 2D spectrum of Theta Leo. We can even see the H-alpha line in absorption. How cool is that? Now we're going to refine the focus in order to maximize the amount of light going through the slit. This is completely optional, but it's quick and easy thanks to a small Python script I created. You can find it in this GitHub repository. Its role is to measure the FWHM and the overall brightness of the 2D spectrum. Let's go through the iterative process of focusing our 2D spectrum. Alright, we are done. Let's see what the result is in graphical form. As you can see, the focuser position at which the light output is optimal is not exactly the one that gives the finest spectrum. That being said, the overall intensity of the spectrum is relatively stable within a fairly large range, so we'll find a compromise that gives us both a bright spectrum as well as sharp stars in the guide camera. All we have left to do is to automate capturing the data in multiple sub-exposures using Nina's advanced sequencer. I use the speckle container, which is made available by the speckle imaging plugin, so that I have full power over subsampling in the sequence. Let's start the sequence now. Now that our sequence has completed, we have one more thing to do, and that is to turn on our neon bulb to capture calibration lines that will be essential in the processing phase. And now we can see the neon lines. It looks kind of like a barcode. We know the precise wavelength of each of those well-known lines, and the processing software will be able to use them to know which wavelength corresponds to each pixel in our 2D spectrum, and that is required in order to generate a spectral profile which looks like that. Alright, just for fun, let's now capture the spectrum of a famous planetary nebula, NGC 2392, also known as the Eskimo Nebula, in the constellation Gemini. I'll speed up the recording and I won't make any comments since we're just reproducing the steps I've already described. I'll be back in a minute. Alright, that's all I have for you today. I hope that you enjoyed this type of content. If you do, please click like because it helps the channel. Also, don't forget to subscribe because we're going to be back in just a few weeks with another exciting video. Until next time, thank you for watching.